of me
All right.
when Adrian came into night class and was like talking to Donnie, and he was like, "Yeah, I'm down for that."
Don't want to be obtuse.
Okay, let's get started. Next section is on random variables.
Okay.
So let's remind ourselves, what is a mathematical model we've been using for probabilities?
No, letters.
Sample space.
Sample space. A sample space. We've been using what's called the sample space. We've been using something called the sample space SP. What is S?
Samples.
No. S and P together as an ordered pair is called a sample space. What is S?
The set of all possible outcomes.
The set of all possible outcomes. In general, it's a non-empty finite set. And we call it the set of possible outcomes. What is P?
The probability.
Our probability function. What is the domain of P?
The set.
Yeah, set.
S is the domain of P. P assigns a probability, a number, to everything in S. It says how likely it is. So if S is heads and tails, then P would map heads to 1/2, and it would map tails to 1/2. It's the probability function. Right? That's P. P is our probability function. What are some properties P has? One, its domain is S. What else do we know about it?
They all add up to 1.
The sum of all the probabilities is always 1. What's the last thing we know about it?
All the values are less than or equal to 0. Can't be less than 0.
All the values are positive numbers, or 0. No negative numbers. There's no such thing as saying there's a negative 13% chance of this happening. That makes 0 sense. Okay, so that's our sample space. So let SP be a sample space and let V be any set. Then, a function that maps from S to any set, doesn't matter. A function whose domain is S, and we're going to call this function a capital X. Don't get confused by that, not lowercase. It's a function. A function whose domain is capital S is called a random variable, or a random variable on the sample space. If it just so happens that B is equal to R, the set of real numbers, then we call X a real random variable. Where this author always says a real valued random variable, I'm just going to call it a real random variable. And typically, that's all we care about, are real random variables. What's a real random variable? It's a function on S that maps each S to some real number. Positive, negative, who knows? Just real numbers. That's all we require. That is a real random variable. Okay. Let's do some examples now. Rolling a pair of dice. So our sample space, S is going to be all the ordered pairs, 1, 1, 1, 2, 1, 3, 1, 4, da, 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 all the way up to 6, 6. We're talking about rolling 2 6-sided die. Okay. What's the probability of each roll going to be? We're going to assume that they're fair dice. What's the probability of me getting a particular roll?
1 out of 36.
1/36. That's the odds of me rolling snake eyes. 1/36. Right? So, the probability for each little s and big S is 1/36. Now I'm going to come up with some new random variable, just off the fly, x. I'm going to make it a real random variable, so it's going to spit out a real number. So x, you're going to give it a roll. You're going to give it a roll. The first die was little a, the second die was little b. And x is going to spit out some real number. In this case, it's going to be the sum of the rules. You're used to using this for when I say, what did you rule? How do you determine what you ruled? You add the two numbers together. Right? So x, in that sense, is going to be what you ruled. It's going to add the two numbers together. But I can come up with some other game and some other definition of what you ruled. Maybe it's the product of the two die. Why do we add the two die together to say what you ruled? Maybe there's some other game where we'd want to take the product of the two die. And that's what you ruled. So y is going to be that. Y takes each roll, and it outspits the product of the two numbers. Okay? Let's make sure you're getting this. What is x of 2, 5? 7. If you rolled a 2 and a 5, if this is the outcome on your 2 die, then x is the sum of those two, which is 7. What is y of the rule 2, 5?
Yes.
10.
10. What is x of 1, 3?
4.
4?
4.
Yeah, 4.
4. What is y of 1, 3?
3.
3. You look confused how we're getting these numbers. So we just defined two random variables for the sample space for rolling 2 die. There's an infinite number of random variables we could have defined. There's no such thing as the right random variable. There's just more useful ones and less useful ones. So if we're playing the game Monopoly, this is going to be a much more useful random variable than y is, where you're taking the product of the two rules. Maybe you don't care about the product of the two rules. Good? Okay. Notation. Now we're going to talk about the probability that x is a particular number. What is the probability that x is equal to a? What is the probability that our random variable spits out a? That is going to equal the sum of all the probabilities p sub little s for every little s and big S, add them all up, where x of s is equal to a. If that s went to a, look at its probability. Add up all those probabilities. Let's look at a concrete example, because I know that's a lot of notation, but what it's saying is very intuitive and what you would have already guessed if you just did it. So going back to ruling 2 die, same example we were just talking about, and x is going to be the random variable adding up the rule of the 2 die. What is the probability that x is equal to 7?
6, 36.
How many rules, how many ways can you rule so that your outcome is a 7?
6 out of 36.
6 out of 36. You can roll a 1 and a 6. They give you a 7. A 2 and a 5. A 3 and a 4. A 4 and a 3. A 5 and a 2. A 6 and a 1. You follow that? So there's 6 ways where our random variable x spits out a 7. What this notation is saying, for every little s and big S, if the random variable assigns that little s a, in our case 7, if the rule is 7, look at its probability, 1/6, or 1/36, and keep adding up all those probabilities. So we're adding up all the probabilities where the rule was a 7. That's what this notation is saying. How did you get that the probability of our random variable equaling 7 was 1/6 or 6 over 36? How did you get that?
There's 6 ways to roll 7.
You added up each of those 6 ways. So the probability of one of those 6 rolls was 1/36. You added that up 6 times. That's exactly what this notation says. You following the notation?
Yes.
Okay, it's dense, I know. Let's try another one. What is the probability that y is 10? So sample space is rolling 2 die. Now y was a random variable. Take the product of the 2 numbers. What's the probability that the product of your rule is a 10?
4
over 36.
2 over 36?
4 over 30. Wait, yeah, 4 over 36.
4 over 36. We got a 2 and a 4. Which one's right?
Me.
How did you get 4?
What else?
10 and 1.
10 then.
Yeah, but
You
you
can't roll a
get 10
10 and
times
do that
1.
die.
You're only rolling 2 6-sided
Oh,
die. What is the probability that if, so I roll 2 6-sided die, what is the probability of that if I multiply the 2 numbers together, I get a 10? It's only 2 36. There's only 2 ways to do that. So there's 2 s's in big S such that the random variable of s was equal to 10. So you added up their probabilities. 136, 136 twice. Make sense? Okay. What's the probability that x is 2?
136.
136. There's only one way for x to be 2. That's if you roll a 1/1. What's the probability that y is equal to 3? 236. You can rule 1, 3 or 3, 1. Good. What's the probability that x is equal to 1? 0. Notice that for most of the things I put here, the probability of x being that thing is going to be 0. Right? What's the probability that the sum of the rules of my two die is 1? What's the smallest number I can rule with 2 die?
2.
2.
Well, yeah.
So I can't rule a 1. Okay. What's the probability that y is equal to 1?
136.
136. And that's me rolling a 1, 1. Make sense? So there's an example of a couple of random variables and how we calculate the probabilities of them. Next. Let's look at another example. This time we're tossing a coin 8 times. We'll assume it's a fair coin. So one of your possible outcomes is heads, 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 heads 8 times. You could have also got heads, heads, tails, heads, 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 tails, heads. Assuming I said 8 letters, not sure. Tails. All right, there we go. Anyway, so this is the set of all of them. How big is S? What's the size of S?
8 to 2 to 8.
Which is?
Massive.
Which is massive, 256. So the size of this is 2 to the 8, or 256. How did he get that?
Because there's 2 choices.
There's 2 options for the first flip, 2 options for the second, 2 for the third, da 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 da. How many times am I flipping?
8.
So 2 times 2 times 2, 8 times. Or in other words, 2 to the 8. Perfect. So what's the probability of any particular flip? 1 over 2 to the 8, or 256. Right? Good. All right. You can create 2 random variables now for this sample space. I'm going to do x of h. This is going to be the random variables that tells me the number of heads in your 8 flips. So if I plug this into x of h, what is it going to spit out? 8, because this has 8 heads in it. If I were to plug this into x of h, what would it spit out? 0, because this has 0 heads in it. And now I'm also going to use x of t for the number of tails. So if I pick some random element in here, let's say h, h, t, h, t, t, h, h, what number do I get when I plug it into x of h? 5. Because there are 5 heads in there. And if I plug that same string into x of t, what do I get?
That's only 7. What?
Am I missing one?
Yeah, you're missing the.
Missing an h at the end. H, H, and that, and there's only 3 tails in there.
That's
Right?
too many.
If you want 5 H's.
Wait. Oh yeah, you're right.
Okay, I'll lose it.
I was thinking 7%.
All right, so here's a real random variable on the sample space. Here's another real random variable on the sample space. Now I'm going to show you an example of just a random variable. Just to give you an example of one that's not a real random variable. I'm going to say z gives me the position of all the heads in a string. It's going to tell me what positions have a heads. Does the first position have a heads?
Yes.
So it's going to have a 1 in the set. Does the second?
Yes.
Yes. Not the third. Yes, the fourth. Not the fifth. Not the sixth. Yes, the seventh. Yes, the eighth. So here's another random variable. Not a real random variable now, because it's not spitting out a real number. In this case, it's spitting out a set. We almost never work with random variables like this, and this will be the only example of a non-real random variable I give you. From here on out, all our random variables will be real random variables. That's what you typically work with. They're much nicer. But this is still a perfectly valid random variable. Make sense? So, see that example? Now we'll never care about it again. Okay. So back up to x of h here. What is the probability now that x of h is equal to 4? Someone impress me. What is the probability that I get 4 heads? This is saying that my flip has 4 heads. What's the probability that my flip has 4 heads?
50%.
No, definitely not 50%. 1 over 16? Is that what you said?
Yeah.
I'd have to look at that. I'm not sure. I doubt it comes out to that nicely. I have 8 flips. 4 of them are going to be heads. I have 8 flips, 4 heads.
2 to 4.
I have 8 flips. We're going to pick 4 of them to be heads. I have 8 flips. We choose 2 of them or choose 4 of them to be heads.
Oh, 8 choose 4.
8 choose 4. How did you ever come up with that? Genius. You have 8 flips. Choose 4 of them to be heads. 8 choose 4. Right? Simple counting. Right? Sorry. That's how many ways. That's not a probability. That's how many ways. That's a big number. Probability can't be more than 1. 8 choose 4 is how many possible ways we could get 4 heads. But now we're talking about the probability of that. So what do we divide by? 2 to the 8 or 256. I'm fine with, you could put both those on your test. I'd be perfectly happy. Okay, let's look at the next one. What is the probability that we have 5 tails?
8 choose 5.
8 choose 5.
Over 256.
8 choose 5 over 256.
That was 8 choose 3.
Or 8 choose 3. Those are the exact same number. 8 choose 5, 8 choose 3. If I choose 5 to take, that's the same as choosing 3 to leave behind. If I choose 5 to be tails, that's the same as choosing 3 to be heads. Right? So, just roll that way to remind you of that little fact. What's the probability that I have 0 heads?
1 out of 2 to the 8.
1 out of 256, or 2 to the 8.
It's that low.
Yes.
To get straight tails.
The probability that I have 0 heads means I flipped exactly tails, 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 tails. So it means I got exactly this flip. What's the probability of exactly this flip? 1 over 256. Or 8 choose 0 over 256. Same thing. That was a terrible 5. 256. Okay. What's the probability that I have 7 tails? Jeez, I worked
8
way
choose
right
7.
Over.
Over 256.
Perfect. What is 8 choose 7?
It's 8. Sure, 7. It's 8. It's 8.
8 choose 7 is the same as 8 choose 1. How many 1 element subsets can I create from an 8 element set? 8. So this is going to be 8 over 256. Or in other words, it's going to be
1 over 64.
1 over 64.
1 over 32.
80.
Or 128.
8 is 2 to the 3. 256 is 2 to the 8. So it's going to be 1 over 2 to the what?
32. 2 to the 5.
32.
2 to the 5. So 1 over 32. Is that what you said the first time?
Yeah.
Okay.
And then I threw out 128.
Huh?
And then I threw out 128.
Ah, you see that I heard.
64, I was bound to hit it.
Yeah. Well, it makes sense.
Well, this makes perfect sense. Because if you multiply that by 8, you get exactly
64 also makes sense.
that. 64, it makes half as much sense. It's like you're twice as wrong. Like you're doubling it somehow. Okay,
Thanks.
next. Let's ask a slightly more convoluted question. Let's say, what is the probability that the number of heads is greater than or equal to 3 and the number of tails is greater than or equal to 3?
Pretty
8
high.
choose 3. 8 choose 3.
8 choose 3 would be, I have exactly 3 heads.
Miss what she
Oh,
said.
right.
8
Oh, I
choose
forgot that.
4. Yeah, all
Oh,
that stands.
of course.
Right.
Plus 8 choose 4 plus 8 choose 5.
Plus 8 choose 4 plus 8 choose 5. Wonderful. There's going to be 8 choose 3 plus 8 choose 4 plus 8 choose 5
How do you get that?
What?
all over
Yeah.
plus all over 256.
Yeah, how did you get
How did he get that? Well, he probably thought something along these lines. If I have at least 3 heads and at least 3 tails, what's the least number of heads I have to have?
that? 3.
What's the most amount of heads I can have?
8.
What's the most amount of heads I can have if I have to have 3 tails?
Oh,
5.
5. If I tell you I have at least 3 tails in my 8 flips, how many heads can I possibly have? the answer is 5. So that's the same question as the number of heads is greater than or equal to 3, and the number of heads is less than or equal to 5. Or in other words, you can have 3 heads, or 4 heads, or 5 heads. All those are valid.
Okay.
Does that make sense?
Yeah.
Here's how many ways I can have exactly 3 heads. Here's how many ways I can have exactly 4 heads. Here's how many ways I can have exactly 5 heads.
Okay.
So here's how many ways I can have one of those 3 options. Divide by 256 gives us our probability. Everyone good there? Alright, so yeah, that was the same as that. I think we're still good here. Okay, next example. Flipping an unfair coin now.
Yeah, we.
This was an identical question to this.
Not really.
Oh, I thought it was. Let's figure out this one then.
So it's always, I don't know.
This says my number of heads is greater than or equal to 3, and my number of tails is greater than or equal to 3.
Yeah.
This says my number of heads is greater than or equal to 3, and my number of heads is less than or equal to 5. That's why I wrote both these, to show you, instead of thinking about this way, think about this way,
Okay,
and it should be
yeah.
easier for you.
Good one.
Well, if you insist. Okay, so now we're talking about flipping an unfair coin. We're going to get to binomial variables and talk about a binomial. Well, we won't talk about distributions, but talk about flipping an unfair coin, and we're flipping it n times. What do we mean by an unfair coin?
You get more.
It's not exactly 50-50, right? So, my coin, we can count up heads or tails, but my probability, we'll say that the probability of getting heads is p. So what's my probability of getting tails?
1 minus p.
1 minus p. If there's a 40% chance I'll get heads, what are the odds I'll get tails?
60,
How'd you come up with that?
100,
1 minus 40%. So 1 minus your probability of heads is always your probability of tails. Good? Okay. So now we're going to make x the random variable that counts the number of heads you get in the m flips. So x just counts the heads. That's our random variable. Make sense?
Okay.
What's x?
The number
You don't know?
and flips.
X tells us the number of heads in our n flips. We're going to flip the coin n times. If I flip the coin 6 times, and there's 2 heads, what is x of that string of 6 flips? X tells us the number of heads in my n flips. Let's say n is 6. I flip the coin 6 times. 2 of them come up heads. What is x of those 6 flips?
2.
2. Just counts the number of heads. That's all x is doing. Nothing tricky.
Okay.
All right. So now we'll say n is 10. So I'm flipping the coin 10 times. Here's one possible string of flips I get. Heads, tails, 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 heads, tails, 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 heads, tails. What is x of that string of flips?
3.
3. It just counts the number of heads. Nothing fancy, right? Good? Okay. Now, what is the probability of that particular flip? What is the probability? I flipped exactly heads, and then tails, and then tails, and then tails, and then heads.
Over 1,024.
Where'd you get 3 from?
Where'd you get 1,000?
1,024 is right. It's 1 over 1,024.
Oh, yeah, 1 over. Sorry.
If I flip the coin 10 times, there's 1,024 different possible outcomes. Where'd you get that? That's 2 to the 10th. I have 10 options for the first flip, 10 for the second, 10 for the third, 10 for the fourth. Sorry. 2 options for the first flip, 2 for the second, 2 for the third. So it's 2 times 2 times 2, 10 times, 2 to 10, 2 to 10 is 1,024. Right? This is one of those possible flips, so its probability is 1 over 1,024.
Isn't it
Wait, homework
unbiased
review.
or a biased coin?
This is a biased coin.
So it wouldn't be that. So it
This
changes.
is what we're supposed to be.
Oh, thank you. This is what it would be if we didn't have a biased coin. This would be a fair coin,
Right.
right? Yeah, she's right. Thank you for reminding me. Forgot the whole point of why I was writing this out. Alright, so this is equal to,
Thanks, Jerry.
now the way that Debbie was thinking about that is, the odds of this is 1/2, times the odds of this is 1/2, times the odds of this is 1/2, and 1/2 times 1/2 times 1/2 10 times is going to be 1 over 1024. But now the odds of this isn't 1/2. What's the odds of getting heads?
P.
P. Look at our probability function. What's the odds of heads? P. P is just some number.
Okay.
Times, what's the odds of getting tails right after heads?
1 minus
1 minus P. Times another tails.
1 minus P.
So now we've had 2 of those. Times,
1 minus P.
so we have another one of those. Times,
P.
so we have another one of those. And when it's all said and done, how many P's am I going to have?
3.
3 P's. How many 1 minus P's am I going to have?
5.
7.
7. Sorry, I was thinking 8 again.
How many letters are there written out here?
10.
10. If 3 of them go to P, how many have to go to 1 minus P?
7.
10 minus 3. Or 7.
Why 10 minus 3?
Because
There's
7.
10 total.
I know, why did you do
If-
10 minus 3? Why didn't you just make 7?
Because I want you to see the pattern in general. So if I would have told you 6 of them came out to P, how many came out to 1 minus P? 4. 10 minus 6. So if I tell you K of them came out to P, how many came out to 1 minus P? N minus K.
Right.
If N's the number of flips.
Yep.
So in general, for N flips, then the probability of some particular flip, if it's N flips, is going to be P to the K, where K is the number of heads we have, times 1 minus P to the N minus K, right?
It's going to be a negative number.
No, it's never going to be negative. Remember, P is a number always less than
1.
1. It's always less than or equal to 1.
So it's a positive.
1 minus a smaller number, number smaller than 1 is a positive number. A positive times a positive, always positive.
I'll make a distribute right here. So P minus P.
P squared is less than P.
Yeah. But then go P minus. Oh, yeah,
Math always works.
okay.
All right, question. What is the probability now that x is equal to 3? What is the probability that in 10 flips, 3 of them are heads with our unfair coin?
P to the
3.
power 3.
Oh.
Oh.
This was for this exact outcome. For this exact outcome, we got this. What about if I would have swapped the h and the t here? What if we were talking about this one? What's the probability of this exact outcome now?
It's still.
It's still that.
Okay.
So the probability of one of my outcomes, as long as there's 3 heads in it, will always be this. So now, what is the probability? This is the probability of one of the outcomes. What's the probability that I get any of those outcomes?
10, choose 3 times that.
Perfect. 10 choose 3 times p to the 3 times 1 minus p to the 10 minus 3. How did he get that? This is the probability that we get one of those flips. So count how many of those flips there are and add up all their probabilities. If I say, what's the probability with 2 dice that I roll a 7, what do? You count up all the ways I can roll a 7, there's 6 of them, and then multiply it by the probability of each one of those, which is 136. Same thinking here. Here's the probability for one of the flips that has 3 heads in it. Count up how many of those flips have 3 heads and add up all their probabilities. You got this probability that many times. Just like rolling a 7 on the dice. You have a 136 probability of rolling a 7, and there's 6 ways you can do it. You have 136 probability of a particular roll, the same way that this was a particular outcome. There's this many ways to do it, or there's this many ways to do it. You following the logic there?
Yeah.
Now what does this look very close to? Oh, before we do that, let's write it out one more time. So now for n flips, let's do it in general. for n flips, so not 10 flips, but now for n, for any number n flips, what is the probability that I have exactly 8 heads?
10 choose N.
And choose.
P to
N choose H. We have n flips, choose H of them to be heads, times
P to the power of N.
P to the H.
P to the H.
P is the number of heads you have.
And is 10.
N times what?
Times 1 minus P to the power of N minus H.
To the power of n minus h. Perfect. And what does that look a lot like?
Binomial theorem.
Looks a lot like the binomial theorem. Go back to the binomial theorem. Remember the binomial theorem. The binomial theorem said 2 letters, you're used to x and y's. I chose p and q's just to match this better. P plus q to the n is equal to the sum from k equal to 0 to n of n choose k times p to the k times q to the n minus k.
Oh,
You see that? Now let's look at the special case where q is 1 minus p. You with me? I'm going to replace q now with 1 minus p. So we have p plus 1 minus p, all to the n, is equal to let's look at this. What is p plus 1 minus p?
1.
1.
oh.
P minus p plus 1 is 1. What's 1 to the n?
1.
1. So this side, when we plug this into the binomial theorem, spits out a 1. Now what does this side say? If I pick a particular k, so if we start with k equals 0 and I plug 0 over here, then what is this giving us the probability of? This piece right here, if k is 0. That gives me the probability that we get 0 heads.
Yeah.
Right? And then if I plug in 1 for k, it gives me the probability of 1 heads. And then if I plug in 2 for k, it gives me the probability of 2 heads. All the way up until we say n heads. So what is the probability that I get 0 heads, plus the probability that I get 1 heads, plus the probability that I get 2 heads, dot, 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 all the way up to plus the probability I get n heads?
1.
100%. I'm either going to have 0 heads, or 1 heads, or 2 heads, or 3 heads, or dot, 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 or n heads in n flips. So the binomial theorem is telling us that the odds that you'll get some number of heads between 0 and n is equal to 1. Surprise, surprise. 100% chance. Nothing surprising about it, hopefully. Follow that? Okay. Let's go back to this scenario now of rolling 2 dice. These are going to be fair die. 2 6-sided dice. Okay? So S is our sample space, 1, 1, 2, 2, or 1, 1, 1, 2, 1, 3, 1, 4, da, 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 all the way up to 6, 6. What's the size of S? 36. 6 squared, 36. What's the probability of a particular rule?
1 out of 36.
1 out of 36, because now we're back to fair dice. We're no longer talking about unbiased like we were up there. Okay. Now I'm going to create a random variable, x sub 1. What does x sub 1 spit out? So I'm going to have one of my dice is red, one of my dice is blue. The red dice we'll call the first die, the blue die we'll call the second die, just so we can distinguish them. X sub 1 always spits out what's on the red die, whatever's on the first die. Spits out the first number you rolled. So x sub 1, when I plug in the rule AB, just spits out A. Make sense?
Yeah.
So that's our real random variable. X sub 2 is going to be another random variable. It just spits out what's on the second die. Now I'm going to create a new random variable, x, in terms of those random variables. I can combine random variables to define new random variables. What is x going to do? It's going to spit out the sum of those two things. The sum of the number on the first die plus the sum of the number on the, plus the number on the second die. Or in other words, x of a particular rule AB is equal to what x1 spits out when you plug in AB plus what x2 spits out when you plug in AB. Making it very explicit here. What does x1 spit out when you plug in AB?
A.
A.
Just spits out A. What does x2 spit out when you plug in AB?
B.
B. So x of AB is equal to A plus B. It's the exact same random variable we defined over here, just now defining it in terms of two different random variables. Showing you that you can combine random variables to give you a random variable. Make sense? Okay. Not meant to be anything that tricky. Let's just make sure you understand it. Let's say that little s is the rule 5-3. What is, this is supposed to be an s here. What is x sub 1 of s? 5. Sorry, not a good distinction between my 5 and my s's. What is x sub 2 of s? 3. What is x of s? 8. Perfect. Continuing with the example, I'm going to ask some other questions. So, don't want to go. I can never see that. Will you look on that and make sure you can see my hand?
You can, yeah.
Okay. So, continuing with the example up to here, what is the probability now that x is equal to 2? What does x give us? The sum of the rules. What is this? 136. How many ways can I roll a 2 with 2 dice?
3.
What do you think? Nod once for yes, twice for no.
Yeah, ask a yes or no question.
He is paying attention. All right. What is the probability that x is equal to 2? X gives me the sum of the roll. What's the probability that I roll a 2 with 2 dice? I'm playing Monopoly. What's the odds I roll a 2?
1 out of 1/6.
Not 1 out of 6,
Or 1 out of
because I'm rolling 2 dice. 136. Okay. So the probability that I roll a 2 is just 136. Very small probability of me rolling a 2. Now, what is the probability of me rolling a 2 if I tell you that the first die was a 1?
Just as.
Back to conditional probability. I rolled my dice. I'm trying to hide it from you. I rolled my 2 dice. One of my dice rolled into your line of sight, and you saw that it was a 1.
Oh no.
What is the odds now that my total rule was 2?
1/6.
Oh, the total roll is 2.
Yes. What is the probability that x is 2 given that x1 is 1? What is the probability that my total rule is 2 given that my first die is a 1? 1/6. So it changed the probability a lot. It gave you a lot of information. These are not going to be independent random variables. All right? What's the probability that x is equal to 2 given that x1 was a 3?
What?
0.
0. What's the probability that I rolled a 2? So I'm hiding my roll from you. I rolled a die. I say, oh yeah, I got a 2, but one of my dice you can see and it's showing a 3. What are the odds I'm lying?
100%.
100%. Or what are the odds I'm telling the truth? 0%. Make sense? Okay, so these are not independent random variables. Knowing information about x1 definitely changes what you know about x. Let's try another one. I roll my 2 dice. What are the odds that my first roll was a 2, given that my second die is a 2?
0%.
1/6. This is now x1 and x2, not just x. x1 is what's on my first die, x2 is what's on my second die. So I roll my 2 die. You can see my second die, you can see that's a 2. I tell you that my first die is also a 2.
Nice.
What are the odds I'm telling the truth? 1 in 6. What if you knew that my second die was a 4? Then what would the odds of me rolling a 2, my first die being a 2, have been? 1 in 6. What are the odds that my first die is a 2, period? 1 in 6. And knowing what my second die is tells you nothing about what my first die is. So these are going to be independent random variables. In other words, the probability that x1 is equal to a, given that x2 is equal to b, is just the probability that x1 is equal to a. Knowing that x2 is b gave you no information about what x1 was. It didn't change anything. Notice that that was not the case here. P of x equal to 2 is 1 over 36, yet P of x equal to 2, given that x1 was 1, is now 1/6. Knowing x1 drastically changed the probability that x is equal to 2. Right? So that's giving you a notion of dependent versus independent. Now we'll create a definition. Definition. let SP be a sample space and let x and y be random variables on the sample space. Then we say x and y are independent, provided that for all a's and b's, then the probability that x is equal to a and y is equal to b is the same as the probability that x is equal to a times the probability that y is equal to b. This is logically equivalent to, we proved this last time using a slightly different notation, but this is logically equivalent to the probability that x is equal to a given y is equal to b is equal to the probability that x is equal to a. This says the same thing as this. Logically equivalent. If knowing something about y doesn't give you any information, they're independent. Or in other words, if the probability that x is equal to a and y is equal to b is just the probability that x is equal to a times the probability that y is equal to b, then they're independent. Knowing one gives you no information about the other. Or in other words, to be more explicit, that's the way the author gives it. I want to be a little bit more explicit to make it clear where these a's and b's are coming from. So another way of saying the exact same thing that I think is more clear. If you know that x is a random variable from s to a, and you know that y is a random variable from s to b, such that for any little a in here and for any little b in here, the probability that x is equal to a and y is equal to b is the same as the probability that x is equal to a times the probability that y is equal to b, then we say that x and y are independent. So two ways of saying the exact same thing. And then this being the case is identical, logically equivalent to this being the case, which is the way we talked about it up here. You go with that? Need an example where we do this? Think about it this way?
Sure.
Okay, let's redo this one thinking about it this way. What is the probability that x1 is equal to, give me a number,
4.
3, and x2 is equal to 4? What is the probability that my first die is equal to 3 and my second die is equal to 4? Well, just answer the question thinking about it. 136. Which is the same thing as a probability that x1 is equal to 3 times the probability that x2 is equal to 4. 1616. So that's using independence a different way. Or it's the same example. Make sense? Cool. Alright, that ends that section. Moving on to the next section. The hard section and the most interesting section. Expectation. Expectation. Give you a quick intuition for expectation. We often use expectation to calculate the odds of a casino losing money over time. We kind of talked about this last time. If I set up a game where you have to pay $1 to play, you flip a coin. If you get heads, I give you $2. And if you get tails, then nothing happens.
You're going to lose a ton.
I'm going to lose a lot of money.
Yeah.
It's $1 to play, so you give me $1. If you flip heads, I give you $2.
So
If you flip tails, then nothing.
Right.
So, in general, I'm going to lose money, right? If I play that game 1,000 times, how much money am I likely to lose? That's what we're going to calculate. That's expectation. Or another way to think about expectation, if I roll 2 dice, what am I most likely going to roll? What's the expected value of my roll of 2 dice? 12? If I take 2 dice and I roll it, and you write down the number, and I take those 2 dice and I roll it again, and again, and again, and again, and again, and we average up all my rolls, what do you think the average is going to come out to? 7. So the expected value of rolling 2 dice is a 7. So that's giving you high-level intuition for expectation here. We'll define it exactly. Let x be a real random variable. So it spits out real numbers. Takes everything in the sample space, or takes everything in the outcome, set of outcomes, and maps it to a real number. Let x be a real random variable on some sample space SP. Then the expected value of x is given by, here's our notation for expected value. We're going to use this 1,000 times. The expected value of x is equal to the sum for all little s and big S of x of s, the number that x spits out when you give it little s. Remember, x is a real random variable, so this is going to be a real number. The number x spits out when you give it little s times the probability of that little s. Let's do this for rolling just one die, rolling a fair die. So you got a fair die, s is 1, 2, 3, 4, 5, 6. What's the probability that you roll a 4? What's the probability that you roll any particular number? Okay, so our probability function says for any little s, it's just 1/6. You with me? What is the expected value? If I were to roll one die 1,000 times, and you were to average out all those numbers, what would you get? I can't even rule a 7. One die.
Oh.
One die. We're rolling one die, 6-sided die, numbers 1 through 6. I roll 1,000 times. What's my average going to be?
That's three.
How do you know?
There's no average. That's 1, 2, 3, 4, 5, 6. Sorry.
What is it going to be gathering around? What's it going to be really, really close to if I do this 1,000 times?
They're all going to be the same. Either 3 or 4. What?
Yeah.
So the average is going to come out to
Oh, all
3.5 of all the rolls. I roll the die 1,000 times, so I have 1,000 numbers.
Think about them added together.
I want to know their average now. How do I get the average of a bunch of numbers?
Add them together and divide.
Add and divide. What's the average of 2 and 8?
6.
What's the average of 2 and 8?
5.
5. How do you get that?
Add them together and
2 plus 8 is?
10.
We added up two numbers. 10 divided by 2 is? What's the average of 2, 8, and 5?
Weird number. 5.
Still 5. 2 plus 8 plus 5 is?
15.
15.
How many numbers did we add up?
3.
So our average was 5, which makes sense. The average of 2, 8, and 5 is?
5.
What's the average of 2, 8, 5, and 5?
16. 5.
20.
5. It's 5.
2, 8, 5, 5.
Yes. What is the average
We
of
said
2,
28 divided by
8,
4.
5, and 5?
5.
The average is 5. What's the average of 5, 5, 2, 8, 5, 5, 5, and 5?
5.
I don't know.
It's 5.
It's 5. Are you sure?
Yeah, positive.
It's like 6
Don't
and a half.
know you know.
Yeah, no, it's 5.
The answer is 5.
Oh, I'm so proud.
5 plus 5 is 10, plus 2 plus 8, that's another 10, plus 5 plus 5 plus 5 is another 15, so we got up to 35. We said 7 numbers.
5. Oh,
5.
yes.
Now what's the average of 5, 5, 5, 5, 5, 5, 2, 8, 5, 5, 5, 5, 5, 5, 5?
5.
I'm gonna
Still 5.
Let's go. You can do that.
Right?
Yeah, I got it. I just-
Okay. What's the average of 2, 8, 2, 8, 2, 8, 2, 8?
5.
5. Okay.
Well,
Averages.
Let's see, like.
So if I roll a 6-sided die a trillion times, some massive number of times, an absurdly large number of times, what is my average roll? What's my average going to be?
3.5.
3.5.
Oh, you cannot roll a 3.5.
No, you can't roll it, but it's going to be your average.
If you add them all up, divide.
Look, let's say that you rolled a 4, then you rolled a 5. What's your average so far? But you can't roll that. Doesn't matter. Your average is your average.
Okay.
Make sense?
Yes.
Okay. So in your average, if you roll a single die an absurdly large number of times, is going to be 3.5. Let's do this just in case it's not perfectly clear.
Roll the numbers.
So we'll say that n is some stupid large number, a trillion. Okay? N is a trillion. So I am going to have a 1, and I need to add up all those 1s. If I roll the die a trillion times, roughly how many of those are going to be a 1? 1/6 of them. So I'm going to get an n over 6 times, whatever that number is. Plus, I'm going to get a 2, n over 6 times, whatever that number is. And I'm going to get a 3, n over 6 times, and a 4, n over 6 times, and a 5 n over 6 times, and a 6 n over 6 times. Oops. A 6 n over 6 times, right?
Yes.
And we're going to divide by n the total number of times I rolled. That's going to be my average.
Yep.
Okay, let's figure this out. First, all these numbers are divided by 6, right?
That's right.
So I can take that 1 6 and pull it out here. So pull the 1 6 out here and get rid of all those 6's. So that just becomes an n. That becomes an n. That becomes an n. Plus 3n. Plus 4n. Plus 5n plus 6n. You with me?
Yep.
All right. So now I have 1n plus 2n plus 3n plus 4n plus 5n plus 6n. How many n's do I have?
21.
20 what?
21.
21? You sure?
Yeah.
Good. 21. 1 plus 2 plus 3 plus 4 plus 5 plus 6 is 21. So I have 21 n over n for the n in the denominator, and we have 1 6 times that. Right? Cancel out n top and bottom, and you get 21 over 6. Which is the same thing as 3 goes into both those, so you get
About 3 times.
7 halves. Exactly 7 halves. Or exactly 3.5. That's your expected value. How do we calculate it? We took, let me rewrite out exactly how we calculated that using our notation that we have up here. Our expected value is equal to the sum for every little s and big S of x of s times the probability of getting that. So that is equal to, x of s was the number that we rolled. So we could have rolled a 1, and we got that with probability what? 1/6. You get a 1 1/6 of the time. Plus, you get a 2 1/6 of the time. Plus, you get a 3 1/6 of the time. Plus, you get a 4 1/6 of the time. Plus, you get a 5 1/6 of the time. Plus, you get a 6 1/6 of the time. What does that all add up to? They're all over 6. So you get 1 plus 2 plus 3 plus 4 plus 5 plus 6, all times 1/6. Or 21 over 6. Or 7 halves. That's what this formula is saying. Make sense? Okay. Will you look on that and see if you can see my finger?
You can, yes.
Yes, okay. So we'll continue and then remember to move back to this. Alright. So let's go back to our favorite spinner. We go back to our favorite spinner. What is the expected value on the number spun?
1.
Or in other words, here's another way to say it. Let's say we set up a game, you spin the spinner. Whatever number it lands on, I have to pay you that amount of dollars. You spin a 1, I have to give you a 1. You spin a 2, I have to give you a 2. You spin a 3, I have to give you $3. You spin a 4, I have to give you $4. How much should I charge you to play this game so that in the average, I don't make or lose any money? $2?
$2.50.
It's kind of important. We're going to take this game down to Vegas. We're going to play it a lot. We don't want to lose money.
$3.
It's going to be your money.
$1.50.
So let's just calculate the expected value rather than all this random guessing. What is the expected value equal to?
25%.
It's going to be equal to the sum of all the different outcomes we can get times the probability of getting that outcome. So I can get a 1 how often?
1/2.
1/2. I'll keep it like this just so you can see where it's coming from. Plus I can get a 2 how often?
1/4.
Plus a 3 how often?
1/8.
Plus a 4 how often?
1/8.
Plus a 4, 1/8. Okay, so what does that equal to? We're going to have a half plus 2/4 is going to be another half, right?
Yep.
Plus 3/8 plus 4/8. That's fine, but 1 and 1 is 1. 3/8 plus 4/8 is
7/8.
so 1 and 7/8. Or in terms of currency, 1 point, what is it? Plus 7/8 is a decimal?
It's
Zero
like
56 or something.
$87 or 87.5.
Is it 875?
I think.
Hey Siri, what's
think
7
you're right.
divided by 8? Yes.
So we would have to charge them at least $1.80. So if we charge them $1.88 to play the game, and we get a ton of people to play the game, we'll very gradually make money.
So you charge them $2.
Yeah, so charge 2, so you automatically.
If you charge $2, you make money pretty quick, but maybe people won't play with $2. Maybe they'll somehow intuitively sense that's not fair.
I think people would play $2.
Huh? One way to find out.
That's just $2.
It's just $2, and you could get 4 to double your money.
Yeah,
I
you
think
bet.
you did like $2.50.
I mean, and there's even like at least a 50% chance you're gonna get all your money back.
Literally.
True.
So yeah, I mean, there's basically no risk. All right, so there's an example using expected value. Go ahead. Oh, go ahead. Next one.
What the heck? There's a 50% chance of getting your money back.
Yeah, there's a 50% chance you get your money back,
So weird.
and you can even double your money. So this is a good game. This is a good deal. $2 is definitely worth it.
For sure. I would play that game.
So
You would?
automatically-
I will play this game with you as long as you would like.
Go play it all night long.
I will play this game all night
It
long.
looks so legit.
All right, well, if it appeals to your
Jen's
intuition,
really buying it.
there you go. You can set it up. Start making money.
Start making money.
You got to go that way till you reach your reservation, but all right, or go that way to Vegas,
Do
Nevada.
a senior activity and just be like, yeah, we should
Yeah.
gambling. Just take money from every student.
There you go.
Stuff like this so that
You can start ripping off students.
3 days 6.
They'll say math isn't worth anything. You can rip people off with it, right?
That would actually be a really good lesson. That would be awesome.
Well, most people aren't going to learn a lesson because, in general, some people are just going to get lucky, and in general, some people just aren't going to get lucky.
Well, we're gonna
No one's going to know that, oh, it's good for you to learn the lesson?
Yeah, we'll teach them why there's lots of people. We'll be like, so we cheated you guys out. We only have a 1.875 chance of getting this.
The expected value was only $1.87.5.
Yeah. And we charge them like $3 and they still take it.
3's pushing it, but I think you could talk them into 2. The logic of 50% chance you get your money back.
Yeah.
Maybe
Yeah,
some
because
people will
if
eat that up.
they gave you 3, you would need an option for 6. To double your money.
What if you did a 6 instead of a 4, but made it $3?
If you did a 6 here,
Yeah.
so putting a 6 there is the same as putting a 6 there. And so now it's $2.12.5.
And I bet
So you
charge
can put a
$3.
6 there, you get charged, $2.50. Do okay.
What if
If you get enough people.
What if you change 3 to 6 too?
So you want this whole thing now to be a 6th?
Yeah.
So then that's the same as 6 over a quarter, which is now $3.50.
So you charge them $4 and you play that game. Yeah.
No one would play that.
I wouldn't play
Because,
that.
like, look, it's 50%
Yeah,
chance
too,
of getting
right.
just $1.
What we did before was better.
Yeah, the way you initially had it, I mean, it seemed like it was working with your guys' intuition. That's all you gotta do is find out what works with people's intuition, but doesn't really work. That's how you get it. All right, anyways, rolling 2 fair 4-sided dice now. And we went to 4-sided to keep the numbers small so that we don't have to get crazy with it. A 4-sided die that has the numbers 1 through 4. So how many possible rules are there with 2 4-sided dice?
8.
You're gonna hurt me. 16. 4 options for the first die, 4 options for the second die.
4 times 4.
A 4-sided die. I mean, you've seen a four-sided die before, right?
Yeah.
It's just 4 triangles.
Pyramid.
No, pyramid has 5 sides.
What do you call
Come-ish.
Equilateral prism.
it? Prison. That's what it's called.
Well,
Prism
prism is just a general term for
3D shape.
Okay, guys,
3D
this is
shape. So
not-
like a rectangular prism is.
Still prison.
So I was looking for a triangular prism. I don't know what it's called. Should know. It's one of the platonic solids.
Yeah, it is.
Yeah, there's 5 platonic solids. 5 solids you can make where every face
there are
has the
6.
same shape. Are there 6? There might be 6.
And then
We can
if
think
you
through it.
count
It's not that hard to prove how many there are, but let's not do it right now.
Why don't you count a coin?
What?
Platonic solids, coins, just six.
A coin? Because it's not a 3D object. The Greeks would call it, well, they'd say that's a cylinder, and one of the faces is not like the other.
7, I guess. Small cylinder.
Anyways, so let's continue with this one. No, I wrote that after the fact. That has nothing to do with this problem. So now we're rolling just 2 4-sided die. And the way that we'll write that down, I didn't want to write out all the order pairs, but you can roll a 1 and a 1, a 1 and a 2, a 1 and a 3, a 1 and a 4, a 2 and 1, 2 and a 2, dot, 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 all the way to a 4 and 4. Make sense?
Okay.
So what's the probability that I get 4, 4?
116.
1/16. Okay, perfect. So now we're going to calculate the expected value of this ink. If we roll these 2 dice, what do we expect our roll to be?
5.
What are you talking about?
If I were to take these 2 die and roll it 1,000,000 times, what would the average of all my 1,000,000 rolls be?
2.
2.5. No.
What?
2.5.
Am I missing something? What, are you not adding them together?
Yes, we're adding them together. So
That is.
I could roll a 4 and a 1,
Oh,
which
yeah.
would give me a 5.
Oh, yeah, sure.
1.5.
I can roll a 2, a 3, a 4, a 5, a 6, a 7, and 8.
Right, I see.
Those are all my options.
So
Everyone understands that it's 5.
Well, let's not just rely on our intuition. Let's calculate it.
1, 4, 2, 3, 3, 2, 4, 1.
So, how do we calculate the expected value?
Add them up.
It's going to be each outcome times the probability of getting that outcome.
Okay.
So, for 1, 1, let me write this out stupidly explicit, just to make sure we are super clear. It's going to be x of, oh, I didn't say what x was. X is giving us the number on the die. It's giving us the sum of the 2 dice.
Oh, well, if you told us that.
Okay, so we're going to be looking at, the expected value is going to be x of the roll 1, 1 times the probability of the roll 1, 1 plus x of the roll 1, 2 times the probability of the roll 1, 2 plus x of the roll 1, 3
Are you going through all of them?
times the probability of the roll 1, 3. And he sees that this is getting super tedious.
Yeah.
But we would keep adding up to dot, 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 plus x of the roll 4, 4 times p of the roll 4, 4,
But
right?
the probability would just be 116.
The probability for all these is just 1/16, right?
Yep.
But, so this would be equal to, writing it out, what is x of 1, 1?
2.
2. If you rolled a 1 and a 1, we say you rolled a 2. That's what x tells us. So that would be 2 times, you said the probability of that roll is 1/16, plus
3.
3 times 1/16, plus,
3. Times 116.
oh, sorry, we're on this one.
4.
Plus 4 times 1/16, plus dot, 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 plus all the way down to this last one is going to be 8. 8 times 1/16. Right? How many of these terms would there be? 16. One for each of the rolls. just trying to make sure you understand this formula explicitly. We're adding up for each thing in S. Here was S. S was all these things. For each thing in S, plug it into your random variable and multiply it by the probability of getting that S. And add them all up.
How is there 60?
Huh?
5 times 6, 116, 6 times 116, 7 times. Where'd the other 8 come from? What?
Okay, let me move the camera first. And then maybe be more explicit about this one. Okay, I can see that. Should be good. Okay, let's be a little bit crazier about it. We don't need this. Can you still see my hand?
Yeah. Yeah.
Okay. All right. So here's our S. S is 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4. Right? And so now we're calculating the expected value. The expected value of X is going to be equal to X of 1, 1 times the probability of 1, 1 plus X of 1, 2 times the probability of 1, 2
Okay.
plus X of 1, 3 times the probability of 1, 3 plus, let's go ahead and, no, I want to do enough that you see the pattern flip. X of 1, 4 times the probability of 1, 4 plus X of 1, 5. Oh, we don't have a 1, 5, so now we go to 2, 1, right?
Yep.
Plus X of 2, 1 times the probability of 2, 1 plus, now I'll do dot, dot, dot. I want to get at least that part. And our last one will be X of 4, 4 times the probability of 4, 4. Okay, so let's write that out now. What is X of 1, 1?
2.
Is that right?
Yep.
We'll worry about it later. All right, so that's giving me 2 times. What's the probability that I roll 1, 1?
1/16.
1/16. Plus, what's X of 1, 2?
3.
What's the probability of 1, 2?
1/16.
Plus, what's X of 1, 3? Plus its times its probability. So I'll get that 1/16 of the time. Plus
It's going to be a lot.
5 times 1/16, right?
Yeah, 116.
Plus
3.
3.
Whoa. Yeah.
That's why I went that far.
Nice.
Plus 3 times 1/16. And then we would do plus 4 times 1/16 would be the next one, right?
Yeah.
Plus 5 times 1/16.
4.
Plus 6 times 1/16.
No, what?
Yeah.
Oh,
Yeah, well, you're right.
yeah.
2 and 4.
2 and 4.
2 and 4 would be a 6. 6 times 1/16. And then we would go to
3 and 1. So
3 and 1, which would be plus 4 times 1/16. And we keep going plus dot, 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 all the way until we got to
8.
8 times 1/16. Okay, so you see how these numbers aren't just counting up to 8.
Right.
And so if we wrote them all out, there'd be a total of 16 numbers.
Okay, that's right.
Okay. And we could calculate this, and that would be kind of messy. Now, what's easier for us to do is to just group all the possible types of rules that give us the same thing. In other words, we have 3/16. How many times is that going to show up?
A lot.
4 3 times?
In this case, it's only going to show up twice.
Why? Yeah.
Oh,
Yeah.
So then it restarts at 4. Oh, yeah.
4.
So we can only get a 2 one way. We can get a 3 2 ways. We can get a 4 3 ways. We can get a 5 4 ways. We can get a 6 3 ways. We can get a 7 2 ways. And we can get an 8 one way, rolling 2
What
dice.
did I say? It's 4, 5, 5. What? 5.
Does this make sense, this counting up right here?
Yes.
So rather than multiplying it all out like that, we can instead say I am going to get a 1/16 of the time. I'm going to get a 2/16 of the time. I'm going to get a 3/16 of the time. I'm going to get a 4/16 of the time.
5 3
Sorry, we started it wrong. We can't roll one. A 2 is 1/16. A 3 is 2/16. A 4 is 3/16. A 5 is 4/16.
6 is 3
A 6 is 3/16.
16.
A 7 is 2/16.
8 is 0.
And
and 8.
an 8 is 1/16. So that is what this next theorem is going to say.
Whoa. Couldn't you?
The next theorem is going to say, rather than having to do it this way, where you write out all the numbers, you can group the terms together like this and add up your probability that way. Pretty straightforward, pretty intuitive, right? It's just a notation, the proof is dead. So that's why I wanted to do one very explicit before the proof so that you don't get lost in the proof. So we're saying that the expected value of x is going to be equal to, for every real number a, do a times the probability of getting that number. Now, most of the times, what is the probability in this case that x is equal to 57? What's the probability that I roll a 57 with 2 4-sided die?
0.
0. What's the probability that I roll pi?
0.
What's the probability that I roll negative square root of 2?
0.
0. So for almost every real number, you're going to be adding up a bunch of zeros. So we only care about the numbers that don't give us a 0. In other words, we only care about the a's for which there's a probability that x could actually equal a.
Why is that not A in the naturals?
Because this is true in general for any real value function x. We happen to be in a special case where everything that's coming out are natural numbers with rolling a die. But it's not just for rolling a die. It could be the expected value of a random number generator on a computer.
Or you could do like a minus.
Yeah, it's possible to get negative things. Anyways, so for the vast majority of the a's, the probability that x is going to equal a is going to be 0, so you're going to be adding up a bunch of zeros, which doesn't change anything. In general, what are we saying? We're saying do 2 times the probability that x is equal to 2 plus 3 times the probability that x is equal to 3. You're just going to add up every a, sorry, up here, every a. You're going to add up a times the probability that x is equal to a. You do that, that's the same thing as calculating the expected value. And it's just regrouping the terms. Rather than having them all list out like this, group all the ones that have a like coefficient there. So group all the 3's together. There were 2. If we looked up here, we would have had 3 times 1/16 and 3 times 1/16. That showed up twice. Group those together. That's all we're doing. Okay, so here's the proof. We're going to prove that the expected value of x is equal to the sum for every real number a of a times the probability that x is equal to a. By definition, the expected value of x is equal to the sum for every little s and big S of x of s times the probability of that s. With me so far? Here's where we just regroup the terms. I say that's the same as, for every real number a, group the terms together in a sum, all the s in s where x of s is equal to a. So when a is 1, group all the terms together where it came out as 1. Where a is 2, group all the terms together where it came out as 2. Dot, 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 do that for every a. Then we would have relisted all our terms. Now grouped together in these smaller sums.
Okay.
Right?
We did.
Which is what we did. Now, did we ever go over that definition? Did I erase it? I don't think we showed this definition. And I think I erased it. Or I forgot to write it. Anyways, so this is just regrouping our summed up terms. Do all the ones where a is 1. Then do all the ones where, where x, if a is 1, do all the ones where x of s came out 1. Then all the ones where it came out 2. Then all the ones where it came out 3, etc. So going from here to here, we're just grouping the terms where x of s came out to the same number. Then going from here to here, we know that for each a and r, x of s is the same thing as a. So just replace x of s with a and factor it out of our sum. if we have the term, if we have x of s in every term in this sum, we can factor it out of the sum. And x of s is the same thing as a. If I have a times c1 plus a times c2 plus a times c3 dot dot dot, that's the same thing as a times c1 plus c2 plus c3.
That's right.
That's all I'm doing here. So I'm going to take x of s, which is the same thing as a in this inner sum, and I'm going to factor it out of the sum. I just pulled it out and rewrote it as a. Because remember, inside this sum, x of s is equal to a. Make sense? Dense notation, but pretty simple what you're doing. So I'll factor out the a. Now this is a definition I forgot to tell you. What do we mean by the probability that x is equal to a? What by definition does that mean? That means the sum of all the probabilities of s, such that when you plug that little s into x, it came out a. That's what we mean by the probability that x is equal to a. It's the sum of all the s's in our outcome space, such that when you plug that into x, it was a. That means the probability that x is a. Add up all the probabilities that x of s is equal to a. Does that make sense? If x is the sum of rolling 2 dice, what's the probability that x is equal to 7? Talk about rolling 2 6-sided dice. It's 136 plus 136 plus 136 6 times. So how do we calculate that? You look at all the places where x is equal to 7, all the rolls that gave us 7, there were 6 of them, add up the probability of each of those 6 rolls. That's the probability that x is equal to 7. What's the probability that x is equal to a? Look at every little s and big S, such that when you plug that into our random variable, it spits out a. Now add up their probabilities. That's the probability that x is equal to a. Kind of dense, but once you see it, it feels obvious. Good?
Why do you get rid of the sum?
Adding up all the individual probabilities is what we mean by the probability that x is equal to a. The probability that x is equal to 7 is equal to the sum for all little s in our set of big S now. Sorry, the blackboard dies here. All little s and big S is all our possible rolls. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. So it's every roll in our big roll, such that that rule was a 7. Or sorry, such that x of s is equal to 7. The rule was a 7. When we plug it into our random variable, it's 7. Add up the probability of each of those. So each little s, that gives us a 7. That would be 6, 1, for example. So what's the probability of 6, 1? 136. That would be 5, 2. What's the probability of 5, 2? 136. Etc. There's going to be 6 of them. So when you add up all those 136 6 times, you get 1, 6. So that sum is what we mean by the probability that x is equal to a. So that gets rid of that sum. Make sense? Okay. All right, going back to the spinner I erased. We got our spinner. Oops. 1, 2, 3, 4. We're going to set up a different game with the spinner now. Our game is going to be, you spin the spinner. If you spin and get an odd number, I give you 20 bucks. If you spin and get an even number, I only give you 10 bucks.
I'll take my chances.
You'll take your chances.
There's nothing.
How much would I have to charge you to keep the game fair?
15.
15?
The expected value. No, it'd be like.
Let's calculate it.
Yeah.
Let's calculate the expected value of the spinner. So our random variable is it assigns to 1, 20, 2 to 10, 3, 20, 4, 10. You get 20 bucks if you spin a 1, 10 bucks if you spin a 2, 20 bucks if you spin a 3, 10 bucks if you spin a 4. Our expected value then is equal to this sum. For every little s and big S, plug that into our expected value and multiply it by its probability. So this is going to be x of 1 times the probability of 1 plus x sub 2 times the probability of 2 plus x sub 3 times the probability of 3 plus x sub 4 times the probability of 4. So let's write that out. What is x sub 1?
50%.
20.
No.
X sub 1 is 20.
Yeah, x sub 1 is 20. X is this random variable. So 20, now what's the probability of 1?
1.
1 half. Plus, what's x sub 2? 10. Times the probability of 2, which is 1/4. Plus x sub 3, 20. Times the probability of 3, 1/8. Plus x sub 4,
10. 10.
times the probability, 1/8. And now we add this up, right?
Alright.
So let's see what we get. 20 times a half is going to be
10.
10.
Weird. 2.5.
Yeah, I don't know. What would be the easiest to do? 10 plus 2.5.
Yeah.
Let's just keep that as 5 halves for now.
Okay.
Plus 20 over 8, what does that give us?
5 halves.
20 over 8 gives us 5 halves. Plus 10 over 8, what does that give us?
Yeah, it does. Weird. 10 over 8.
10 over 8, yep.
1 and 1. 2.5.
Keep it in terms of fractions, 5/4. All right, so 10 plus 5 halves plus 5 halves is
10.5. No.
what's 5 halves plus 5 halves,
10 halves.
which is
5. So
5. 5 plus 10 is
15.
15, and then we have another one, 16, with a quarter remaining.
16.25.
So we would have to charge $16.25 to play the game if we want to make money.
People would never take that.
That makes sense.
So that one's not intuitive, so let's not play that game.
Yeah.
But
No.
what if you put the 10?
Would they play the game?
What if you get?
No.
You get $20 if you get that or that.
Yeah, so either, yeah.
So you have more than a 50% chance of making your money back and then some.
So make them pay $17 for 18.
I don't know. Whatever would filter their intuition.
It is not. I would never play that game.
All right.
That was messed up.
Okay. We made our game.
I think I take my chances at least.
All right. Let's try just another random variable
Okay.
to make sure you're getting comfortable with these and can do your homework.
Yeah.
So let SP be the sample space for rolling 2 dice. Now we're going to make a random variable x. What does it do? It gives out the absolute value of the first roll minus the second roll. All right?
Alright.
Let's make sure you're getting this. If I did x of the roll 2, 6, what would that equal?
4.
4. 2 minus 6 is
4.
2 minus 6 is
Negative 4.
absolute value is
Positive 4.
okay. That's what x does. Takes the difference of your rolls and then calculates its absolute value.
Okay.
You can take the values and it gives the distance between the two numbers. Okay. What is the probability that x is equal to 0?
We're rolling 2 dice, it's 0.
You're rolling 2 dice.
It's not
That's
0.
same dice.
That's 1 6.
So it's the odds it's the same.
1 6.
What are the odds that x is a 0? When is x 0?
When they're both the same number.
When any of you are the same number. If I rolled a 1 and a 1, that's 0.
Yeah.
If I rolled a 2 and a 2, that's 0.
So,
So how many ways can I do that?
1 6.
6 ways, so 6 over 3, 6 or 1 6. Okay, how many ways can x be a 1?
One is greater than the other.
When 1 is greater than the other, that means 5 4 3 2 3 1. Or you can do 1 and 2.
How many are there?
1 2 3 2 1
Maybe I'll write this as 6 over 36
2
to help us.
2 3 3 4 4 5 5 6 10.
It's 24 over 36.
10 over 36.
10 over 36.
10 over 36. What are all the rules? I can do a 1 and a 2, a 2 and a 3, a 3 and a 4, a 4 and a 5, a 5 and a 6. Or a 2 and a 1, a 3 and a 2, a 4 and a 3, a 5 and a 4, a 6 and a 5. So there's 10 out of the 36 ways here. Okay, how many ways can we get 2?
Is this
Choose. It's probably like 8 out of 36.
going to
It's just 8 out of 36, right?
Yeah. No?
You can roll a 1 and a 3, a 2 and a 4, a 3 and a 5, a 4 and a 6. And then all those in reverse. So it's 8 out of 36.
What about,
How did it get less?
There's less ways for your difference to be a 2 than your difference to be a 1.
yeah, that makes sense.
There's one less.
Just count them. All right, how many ways can your difference be 3?
6 over 6.
Keep going.
No, it's not.
2 to 5, 3 to 3.
636. That's not it. That's true.
6 over 36.
6 out of 36. You can do a 1 and a 4, a 2 and a 5, a 3 and a 6, and then all those reverse.
Choose messed me up.
All right,
Choose.
how many ways can you have the difference be a 4?
The same as 2.
1 and 5, 2 and 6. 4 over 36.
4 over 36.
4 over 36, I said.
And then how many ways can you have the difference be a 5?
2 over 36.
And how many ways can you have the difference be a 6?
1.
1.
1 way. How can you have the difference be 6? What would the dice be?
One of them would be 7, the other one would be 1.
A 1 is 7, 1, 2, 6 side die. All right. So this is all. Now, if we were right, all our probabilities should add up to
36?
36.
1, but yeah, 36 in the numerator, right?
Yeah.
Yeah.
So 6 and 10 is,
16,
plus 8 is,
30, 24,
plus 6 is,
30,
plus 4.
34, 36.
Ah, so good chance we did right.
Lo and behold.
So, quick sanity check there. And, oh, we were doing the expected value of all this now. Sorry. So now, what's the expected value of this thing?
1. Of the difference of the whole thing.
What is the expected value of x now?
1. Would most often be 1.
It's going to be 0 times the number probability of 0, plus 1 times the probability of 1, plus 2 times the probability of 2, dot, 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 plus 5 times the probability of 5.
Right.
Right?
What?
So it's 6 over 36. 10 over 36.
What if you were rolling a dice that had 1s on all sides, and then you put it in the same function? Wouldn't it say the expected is 0 because it's 0 times?
If both your dice
They're added.
just had 1s on it, with x being the difference of the die, then yes, your expected value is 0. You will always get 0.
Actually, that makes sense.
It does make sense. Your average rule will be 0. If this is how you calculate your rule,
Okay.
right? But now back to this example, let's figure out our expected value. Our expected value is, we can get 0. What's the probability that we get a 0?
6 over 36 or 1 6.
1 6. Plus, I guess we can keep everything in terms of 36 just to see where the numbers came from. 6 over 36. Plus, what's the probability that we get, or 1 times what's the probability we get a 1?
10
36.
1036. Plus 2, we get that how often? 836. Plus 3, we get that how often? 636. Plus 4, we get that how often?
436.
436. Plus 5, we get that how often? Oops. 5, and we get that 236 a time. Okay, so our expected value then is going to be equal to, let's just count the numerator. We have 10 here, plus 16,
26.
26, plus 18,
30.
44.
44.
44, 44, plus 16,
60.
60.
60.
plus 10.
70.
So 70 over 36. Let's double check that one more time just to make sure we didn't make a mistake. This time we'll go the other way so we don't follow the same pattern. So we have 10 plus 16 is 26, plus 18,
34. 44.
44.
44, plus 16,
60.
plus 10.
It's the same thing.
Same pattern both ways. That was interesting. Did not anticipate that. Okay, so 70 over 36, which is going to be a little less than 2, right?
Yeah.
2 would be 72 over 36. So just under 2. So you can have someone play a game like that. You give them 2 6-sided die and you say, you win the difference of your roll. So if they roll a 6 and a 1, they get $5. If they roll a 2 and a 2, they get $0. You charge them $2 to play and you'll make money.
A little bit of money. Make
A little bit of money.
It's like
You get a lot of people to play a lot of times.
I think that's fun.
Super fun. Now, calculating these expected values for multiple dice roll kind of gets a pain. So what if I said, you take 2 dice now and you roll them, 2 6-sided die, what's the expected value? You know it's 7, right?
Right.
2 6-sided die, what's my expected value? 7. But now, I don't want to calculate that. That would be a nightmare. I have to do 1 times the probability of rolling a 1 plus 2 times the probability of rolling a 2, plus 12 times the probability of rolling a 12. Right?
What? Yeah.
If I want to calculate the expected value for rolling 2 dice.
Yes.
Now say I wanted to calculate the expected value for rolling 13 13-sided dice.
Why is that?
A 13-sided dice.
I have 13 13-sided dice, and I want to calculate the expected value. Now that sounds like a nightmare, doesn't it?
Sure does.
It sure does. So let's do a cool little theorem now that will save our bacon when it comes to calculating these types of things. This theorem says that the expected value of x plus y is just equal to the expected value of x plus the expected value of y. So we'll do the proof, and then we'll see why this is so useful. So let's see. The expected value of x plus y is equal to the sum, just using the definition, for all little s in big S of x of little s plus y of little s, all times the probability of little s. That's just plugging it in exactly to definition. Instead of my random variable being x, my random variable is x plus y. So replace the x here with an x plus y.
Okay.
You follow that? Okay, now this is equal to, distribute this over these 2 terms. This is equal to the sum of, put square brackets here, x of s times p of s plus y of s times p of s. Follow that? Same sum for all little s and big S. Just distribute that over those. And now I'm just going to break the sum into 2 sums. In other words, if I have a1 plus b1 plus a2 plus b2 plus a3 plus b3 plus, and I keep following that pattern, that's going to be the same thing as a1 plus a2, a1 plus a2 plus a3 plus plus b1 plus b2 plus b3 plus . Right? So I can add up all these terms first, and then add up all these terms. So that's what I'm going to do. I'm going to add up all these terms first, and then add up all these terms. So this is equal to the sum for every little s in big S. My dia's grade 3. For every little s in big S of, put square brackets here to mark our sum. X of s times p of s. So that's one sum. And now I'm going to add that with the second sum, which gives me all my y terms. For every little s and big S of y of s times p of s. Okay. Now that is just equal to, this right here is the exact definition of the expected value of x plus, and this right here is the exact definition of the expected value of y. See that?
Yep.
So that proves that the expected value of x plus y is equal to the expected value of x plus the expected value of y. Why is this so useful? Well, let's say that x is the expected value for when I roll one die. Or sorry, x is the random variable for when I roll one die. So we already calculated the expected value of x. What is that? For when we roll one die, what was our expected value? What was the first thing we did?
3.5.
Down here, it was 7/2. That's the expected value for when you roll just one die. So what's the expected value for when I roll two die? What's the expected value of x plus x? Well, that's the expected value of x plus the expected value of x, which is then going to be equal to,
So you get the value of x times 2.
which is going to be equal to 7. Right? So that's the expected value for rolling two die.
Yep.
What if I had you roll 100 die? What would the expected value be?
Massive.
100 times.
You should be able to figure it out.
7 over 2 plus 7 over 2 100 times.
No, it'd be
What is it?
3.5.
350. 3.5 times 100. 350.
She's on fire.
100 times 7 divided by 2.
That's another way to do it.
Sorry.
You got 7/2 100 times.
Yeah.
So now you don't need to try writing that out, which would be an absolute nightmare. This theorem, very useful. Okay, next theorem. Expected value of a constant of x. The next one here, we're saying that the expected value of some constant times our random variable
Equals constant.
is equal to a constant times our expected value.
So is expected value can be with associated.
So in other words, if I say we're going to play a game with the die now, and whatever you roll, we double it. So x doubles your roll. If you roll a 1, we count it as a 2. If you roll a 6, we count it as a 12.
Not the total, just the rolls.
We're going to say you're rolling one die. So scenario, you're rolling one die. So you can roll the numbers 1 through 6. Our expected value, x, is just going to spit out double your roll.
Okay.
What should the expected value of the one die be now?
7.
Of rolling the one die. Your expected value is now 7.
Yeah.
Yeah.
That's what we're going to prove.
Okay.
We're going to prove that if you take x and scale it up by c, then your expected value is still going to be c times the expected value of just x. That make sense? So if we double x, we double our expected value. Does it make sense what we're doing? Do we need to write out x explicitly? If s is equal to the numbers 1, 2, 3, 4, 5, 6,
You're just doubling it?
and x just spits out s, x of s is equal to s, then the expected value of x is just 3.5. We've already done that,
Yeah.
right? Now what if we put a 2 times here? So then you get 2 times s. In other words, if you roll 1, we count it as a 2. If you roll 3, we count it as a 6. If you roll a 6, we count it as a 12. Now what's the expected value? We're proving that the expected value of 2 times x is just equal to 2 times the expected value of x. We know the expected value of x is 7/2, so double it, it's going to be 7. That's what we're proving in general, rather than just a special case. Okay, so let's prove it. So the expected value of c times x is by definition equal to the sum for all little s in big S of c times x of s times the probability of s, right? Just plugging in the definition of expected value. Just its exact definition. Whatever you have here, plug in s to that thing for each little s and big S, multiply it by the probability of getting that thing. So take that, put it there, plug in your s's, multiply it by p of s for each one. Okay, now you have c times every term in a sum. What can you do if every term in a sum has a common factor?
You pull it out.
You can factor it out, not cancel it out, you can factor it out. So factor it out a sum. This is going to be c times the sum of s for all little s and big S of x of s times p of s. But now this piece right here is exactly what we mean by the definition of the expected value of x. Nice and simple. Okay, last proof we'll do today. Let's prove linearity. Linearity. A and B are constants. So if I do the expected value of x multiplied by some constant a plus y multiplied by some constant b, that's equal to a times the expected value of x plus b times the expected value of y. Operations that preserve that property right there, we call it linearity. A lot of things preserve it. Basically means that they work well with matrices.
Just both of the proofs put together.
Yep, it's just both of the proofs put together, exactly. So the expected value of ax plus by, remember x and y here are functions, is equal to, using our first proof, that's the expected value of a times x plus the expected value of b times y, which is equal to, then using our second proof, a times the expected value of x plus b times the expected value of y. And we're done. That's linearity. Okay, so the expected value of a sum is equal to the sum of the expected values. The expected value of a constant times x is equal to that constant times the expected value of x. And you can probably guess some pretty obvious things that follow from this. If I have the expected value of x times y, that's going to be the same thing as the expected value of x times the expected value of y, right?
Yes.
So let's see an example of that. So here's our sample space. S is going to be, we just flip a coin twice. So S is going to be either heads, tails, heads, or tails.
Okay.
We'll assume it's a fair coin, so the probability of each outcome is just 1/4. You with me? Now x of h is going to count the number of heads, x of t is going to count the number of tails. Let's just make sure we're getting this really quick. What is x of h equal to?
2.
2. What's x of t of h equal to?
0.
0. Make sense? Okay. So now, let's calculate the expected value of h. Or the expected value of x of h. What does that equal to? That's going to be equal to x of h of heads times the probability of heads plus plus x of h of tails times the probability of tails, right? Just using the exact definition. So what is this equal to?
1.
How many ways can I, or what is x of h of hh?
2 and 1/4.
2 times 1/4. Now, we're going to do ht.
1 and 1/4.
1 and 1/4. Now we're going to do th.
1 and 1/4.
1 and 1/4. And now we're going to do tt.
0 and 1.
And so the expected value of it is going to be what then?
1.
1. Right? A half plus a fourth plus a fourth is 1. Okay, let's do the expected value now of x of t. So we'll start with HH.
Oh yeah, 0.
0.
0 times 1/4.
It's gonna equal 1.
Now let's do HT.
1 and 1/4.
1 and 1/4.
1.
Now let's do TH. 1 and 1/4. Now let's do TT.
2.
And all together it equals 1. Okay, so just make a note of that up here so we have space again. The expected value of x sub h was equal to 1. The expected value of x sub t was equal to 1.
You have space for that down there.
Wow. Doesn't matter. Okay, so now we want to look at the expected value of x sub h times x sub t. And what do we think it's going to equal?
1.
2, 1.
1. Okay, so we're all on the same page. So let's figure out what this equals. So this is going to be x sub h of hh times x sub t of hh times the probability of hh. And then we'll continue with that pattern, right?
Okay.
So let's write it out down here. So x of hh is going to be 2 times x sub t of hh is going to be 0 times 1/4. Okay, now let's do ht. What do we get with ht?
1. And
ht.
1 and 1/4.
All right, now let's do th.
1, 1, 1/4.
And now let's do tt.
0, 2.
Okay, perfect. So now that's equal to, this whole term goes to 0. This whole term goes to 0. This is 1/4, 1/4, 1/4 plus 1/4 is 1/2. Not 1. So in general, this does not hold. You can't just do that.
Correct.
The expected value of a product is not the product of the expected values. And it turns out that this will only hold if your variables are independent. And in this case, they definitely are not independent. If you know how many heads you have, that definitely gives you information about how many tails you have. If I tell you I have 1 head, how many tails do I have?
And 2 coins.
Yeah, 2 coins. If you know I have 1 head, you know I have 1 tails. So they're not independent. Information about one definitely gives you information about the other. You see that? So this is only going to hold with independent ones. Now, one more thing you might need before you start your homework is you're going to see a mu symbol all the time. Mu is just shorthand for the expected value of x.
That's what mu looks like.
Mu? Yeah. Sorry, it looks like a U, not an M.
It was mu.
And so
What comes up?
here's the letter U, here's the letter mu.
There. Okay.
Okay.
So you'll see a mu all the time, the Greek version of U, and that's shorthand for expected value of x, or the average, the mean, the weighted average. These are weighted averages. Okay. Any question about any of that?
No. No.
Cool, cool. End it there, and we'll see you guys next week.